So thank you for having me. This is the first work I do with my group in PAC Bayesian methods. This is a work together with my PhD student, Imma Curato. In reality, what we work on is designing model for spatio-temporal data. We work with a class of models that is called mixed moving average field. This gives the meaning of the acronym we use in the title of our methodology. And we think that these models are very general, very versatile for modeling spatio-temporal data. The problems is that in the moment in which we want to use them for a forecasting task, we typically fail to use them. And this is because often we do not know the likelihood function of our models apart for the Gaussian specification. So MMAF guided learning is a PAC Bayesian flavored methodology to forecast data of this kind. We call them a raster data cube. This is a particular spatio-temporal data set. Each record is indexed with respect time, latitude, and longitude. This data typically recorded on a regular grid in space and a regular grid in time. And it's nice to typically represent them as a sequence of frame, and we call each spatial time position as a pixel for simplicity, because this is how we imagine our data. There are many examples of raster data cubes available nowadays in different fields. And what a frequentist approach will be to use this data for a forecast task will be selecting a family of random fields, typically in a parametric form, use this data for estimating the parameters. And this, of course, will give us a complete specification of the random field generating this data set. And then what we would like to know of our random field is a lot of information about its distribution, because this will allow us, for example, if we fix on us in a point in this pixel, for example, to do the task of predicting in this spatial position one time ahead what can happen through the specification, what we call the predictive distribution in this field, that is the conditional distribution of the field in a specific spatial position, specific time, given some past neighborhood information of the field. Of course, this is only possible when you know everything about the field. You know its distribution. But in reality, this doesn't really happen, because the data, I mean, how do you even choose this random field? The problem is the data set we want to work on. This data set has a very complex area coloration structure. Typically, this data can have short or long memory along the dimension, latitude, longitude, time. What I mean with this is that if you compute the correlation function of this data along a certain horizontal vertical direction, the correlation function can be summable or not. So this is what we call short or long memory. And it's very difficult to understand what is the distribution of this data. So we wanted to develop a methodology that is capable, for example, doing this kind of simple task is a big word, but a task that should be easy to understand. So we fix a spatial position in our frame. So we choose a pixel and we would like to make a prediction one time ahead. And we wanted to do this without constraining us to specific information about specific choices on the distribution of the data. We wanted to do it just asking certain moment assumption on the data generating process. And we can do this by at the end, using our data in a particular way. So we have to do a specific embedding of the raster data cube to do this forecasting task. And at the end, in order to make it happening, we are using a generalized posterior. And at the end, by sampling this generalized posterior, we are capable not really of approximating the predicted distribution of the data, but to create, in any case, what we call an ensemble forecast. So even if we do not choose the model, we choose a class of models. What does it mean? We do not choose the distribution, but we need to say something about the underlying data generation, especially because we need a minimum of understanding on how we model the serial correlation of the data. When we speak about space-time, the difficult thing is that different than when we work with IID data or time series. It is a bit lost the concept of what it means a past. So if we want to do a forecasting task in space-time, we have to have a concept that allows us to understand if we are in a specific space-time position, how to use the data basically that we had up to that point. So the underlying data generation we assumed our data to follows as implanted inside a causal model. And this model comes from, so it's inspired by relativity, and now we model the path of lights in space-time. But basically, we work in Euclidean spaces. And what we do is, if you have an observation in this specific space-time point, we consider that the only space-time point that influence the value of the data of the field that we observe in that point belong to the past light cone. So we use this kind of geometry to identify what points influence the data that at the end I observed. And if I am fixed in this space-time point, everything I can forecast is not going to be, so I cannot use my data to forecast any kind of future, but just a space-time point that belong to the future light cone. This is a concept of causality that is called potential outcomes framework, and it has been first described by Rubin in 1974. So the methodology is very general work for the entire class of mixing moving average field, but I wanted just to give you an example from top to bottom on how actually we make this forecast starting from the data. So first of all, we, as I said, we have an underlying model that is a random field that looks like this. It is defined in continuous time and continuous space. So that's the reason also because it allows us to handle different kind of data sets. It is expressed in an integral form. It's an integral on a cone of a deterministic function. And we integrate with respect to a random measure. The important things of our data generating process is that I don't say anything about the distribution that this data set has to have. Just I know, for example, that if I choose this class of model, I'm going to have short memory data. Typically, this is how we choose the mixing moving average field, depending on this empirical analysis that we do before the data. So this model has two parameters popping in. One is inside the kernel function, and knowing this parameter helps us to understand how the correlation of the field is going to decay. And there is the parameter C here. And learning this parameter helps us to understand the causal structure of our model. And I worked a lot in this area before working in forecast, so we have methodology for estimating from the raster data cube this parameter. And this is the first step, in fact, of MMAF guided learning. We take the raster data cube, we assume that it's generated by a specific MMAF, and then we estimate the parameter CNA. Then what we do is taking our data set and extracting a training data set in the fashion of supervised learning. So we want to construct examples that have input and output. In the output, we are going to stack specific value of our data set in fixed time position. So as you can see, the output is identified by the red pixel and is always identified the same space position. And then we obtain the input by a discretization in time and space of the cone of the past that we know containing all the time indices influencing the formation of this specific data that we observe in that point. We extract these cones, and so we form a training data set. This training data set is designed such to preserve the dependent structure of the data because we have to construct it in a particular way. This is the reason because we need to follow this lexicographic order, and this embedding is depending on two parameters P and A that help us to design the code. At the end, we get this training data set, and we can assume that it's generated by a a sequence of identically distributed examples, which we know very well in reality, a lot of information regarding the dependence. So then, once we have a training data set, even if I still didn't say you how to actually determine the parameter A and B that they give it to us for real, we are going to go in a supervised learning setting. So I'm going to use a Lipschitz function. We work with linear function if we follow neural network at the moment to predict at the end the value of my field in a specific spatial position. We've seen a lot of PAC bias today, so I just tell you what is the choice of our loss. Our loss is the absolute loss for reasons that are due to the fact that we need to introduce our dependent structure in our calculation. We need to truncate this loss. And this is our notation for the generalization error and the empirical error. At the end, this is our PAC Bayesian bound. The techniques used for determining it are very standard, but we have decided upon a certain kind of techniques rather than others, because we wanted to make appear in our bound what we call the theta X coefficient. Theta X coefficient is the theoretical machinery that we use to have an account of the dependent structure of our data. There are two divergences popping up in our bound, that they are the KL divergent and the chi-square. This dependence coefficient is at the end, there's its own definition, and you find more information about this if you're interested in this paper. At the end, we also want to put up an optimization task out of this bound, because we would like to, given prior, optimizing this bound for getting my posterior. So we are doing it right now for Gaussian families, and this is how our bound looks like for exponential families. So when we are using for the chi-square the Taylor approximation, so we put it equal to 2 times the KL divergence. And there are many parameters popping up in our methodologies. The red one are hyperparameters that for the time being we fix at the beginning of our methodology. We have that, I told you already, we have estimated this parameter before, and we do this because at the end, there is something important to do before even starting our optimization, is using this bound to setting up our spatio-temporal embedding. And we do this by selecting the parameter A that tells me the distance between the cone in my embedding, by assuming that this coefficient is bounded by this quantity. This is a short memory model, so this coefficient are exponentially decay. I know lambda because I can get to this parameter knowing this capital A in this context. P was an hyperparameter. I assume that this theta coefficient is of order 1 over square root of m, and I know this because I need my PAC Bayesian bound to have each advent order 1 over square root of m. That is the best we can do at the moment. And so it's how we choose A. Once we have chosen A, we have our training data set, and we use it for starting by a standard normal prior, optimizing this bound, and in the family of the Gaussian distribution. And at the end, the way in which we do forecast is very simple. So once we have learned the distribution of the parameters, what we do is rolling our codes. So, for example, if you consider that it's a 2D example and the blue stars are your training data set, and I'm using a past cone for my embedding where there are just 3 stars, in the moment in which I am in this spatial position, and with my methodology, I'm learning a Gaussian distribution for the parameters that help me to make prediction in one time ahead point. And at the end, I'm going to use my Lipschitz predictor with a parameter B drawn by my posterior, and I'm going to feed in it just the same, in this case, the 3 stars, they are the end of my data set. So I really rolled the window on my cone in the embedding for making my, my forecast. And what we obtain at the end is we repeat this process typically 50 times, and we obtain what we call an ensemble. So this is the last slide and also our biggest open questions at the moment. What actually we forecast with our ensemble? So there is just one case in which we really know the predicted distribution of the data in this framework, and is when the model we use is Gaussian distributed. And in this situation, we can sample data from it. So we did it. We sampled 2,000 frames. And in this case, we know the predicted distribution that you see in all of these 6 plots with the green symbols. And what we plot here are the quantile ranges of the predicted distribution, the 95 quantile ranges and the interquartile range. And around what is our test data set? It is a test data set constructed for 200 pixels. The red intervals are given by the Gibbs distribution that we consider our benchmark and doesn't optimize our bounds, but we constructed for the linear case. And then you see in dark green the quantile ranges of different neural network whose parameters have been sampled from the Gaussian posteriors we obtained by minimizing our PAC Bayesian bound. And what we are observing right now is that more parameters, so we wanted to study the effect of over-parameterization on our optimization and the quality of our ensemble. And what we notice is that, for example, more parameters we get, the more it seems to us in all experiments we have so far done, that the interquartile ranges are centering with respect to the predicted distribution. You see it very well in this slide. So the way in which we try to evaluate our ensemble forecast, because we do not have so far a better theoretical framework, is to compare it with respect, empirically, of course, with respect to empirical quantile range of the data generating process. This is more or less our what we are working a lot on, and if you have any input on a theoretical framework that could help us to evaluate our ensemble forecast performance, yes, we would be very happy to hear from you in these days. Thank you very much for your attention.
We have time probably for 1 or 2 quick questions before the next session starts.
Okay. So one of the PAC bounds you showed had a chi-square divergence in it.
Yeah.
Presumably because there's data dependence. Presumably this comes from the dependent data. So is this basically the same result? I know you have a paper with.
Yeah, it is actually, okay. This piece of the puzzle comes from the use of the style bound.
Okay. So you're compounding like the independent component, that's the KL, and the dependent. The only difference is that in the style framework comes out the sum of the theta coefficient will come out this kind of sum of coefficients. And this is done, there were too many for us to optimize, so we needed just one. This is a little bit, I think, I don't know, I cannot say if it is tighter or not with respect to that, but it's the same technique, so it is exactly that.
I think that's all the time we have, but thank you so much.